Chapter 9 of the ABCs of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The ABC of Atoms by Bertrand Russell. X-rays. Everybody knows something about X-rays because of their use in medicine. Everybody knows that they can take a photograph of the skeleton of a living person and show the exact position of a bullet lodged in the brain. But not everybody knows why this is so. The reason is that the capacity of ordinary matter for stopping the X-rays varies approximately as a fourth power of the atomic number of the elements concerned. Thus carbon, whose atomic number is 6, is 1,296 times as effective as hydrogen in stopping X-rays. Oxygen, whose atomic number is 8, is 4,096 times as effective as hydrogen. Nitrogen, whose atomic number is 7, is 2,401 times as effective as hydrogen. Calcium, whose atomic number is 20, is 160,000 as effective as hydrogen. The human body consists mainly of carbon, oxygen, nitrogen, and hydrogen, but the bones consist mainly of calcium. Consequently, X-rays, which go through the rest of the body easily, are stopped by the bones, with the result that we get a photograph of the skeleton. Lead, of which the atomic number is 82, is about 45 million times as effective as hydrogen, and about 280 times as effective as calcium. So it no wonder that bullets come out clearly in X-ray photographs. In this chapter, we shall be concerned with the physical nature of X-rays, not with their application to medicine. When swiftly moving electrons strike ordinary matter, which happens in the case of so-called cathode rays and beta rays, they give rise to X-rays, which were discovered by Röntgen in 1895. It was not known until 10 years later whether these rays were longitudinal or transverse. Then Barclay showed that they are transverse like light, and it is now known that they only differ from light by their very much greater frequency. When a body is hit by X-rays, it gives out X-rays itself, which are called secondary X-rays. These in turn give rise to tertiary X-rays. The X-rays emitted by a body are of two sorts, partly mixed and having no particular relation to the body which emits them, partly characteristic of the body. It is only the latter that can be said to have a spectrum belonging to the substance of which the body is composed. The characteristic X-rays emitted by an element, when analyzed, are found to consist of only a few sharp lines, giving a very simple spectrum, which varies in a perfectly regular manner with the atomic number. Unlike the optical spectra, the X-ray spectra of different elements are closely similar, with an increase of frequency in corresponding lines as the atomic number increases. Broadly speaking, there are three lines, the K, L, and M lines as they are called, which make up the X-ray spectra. But technical difficulties make it impossible to observe more than two in one element. None can be observed in very light elements. The K line cannot be observed in very heavy elements, and the M line can only be observed in very heavy elements. But this is fully accounted for by the difficulties of observation. X-ray spectra can only be observed by means of suitable crystals, and the observations are limited by the crystals that are available. There is every reason to believe that, if we could invent suitable apparatus, we should find that all three lines exist throughout the series of elements. They are, in fact, roughly the same as the principal lines in the hydrogen spectrum, which in that case fall in the optical region. The frequency of each line increases very nearly as the square of the atomic number as we pass from one element to another. Each line corresponds to a transition from one ring of electrons to another. What may be supposed to happen when X-rays are excited is closely similar to what happens when visible rays are excited. An electron, passing M, the cathode stream, which consists of swiftly moving electrons, penetrates into the inner rings of electrons and manages to knock out one of the electrons in an inner ring. The resulting state of affairs is unstable, and presently the outer rings supply an electron to the vacant place in that inner ring. The result is that the atom loses energy, which spreads out in a wave just like a light wave, but when heavy atoms are concerned, the great charge on the nucleus causes the time of revolution of the near electrons to be much less than in the case of hydrogen. Roughly speaking, the number of revolutions per second in an orbit having given quantum numbers will increase as the square of the atomic number of the element concerned. It follows that this applies also to the difference of energy between two different rings, and therefore, by Planck's principle, to the frequency of the corresponding spectral line. For, by Planck's principle, when an electron jumps from one ring to another, the frequency of the corresponding spectral line is obtained by dividing the loss of energy by h. Thus, roughly speaking, we should expect X-ray spectra to give the same line for different elements, only with frequencies that increase as the square of the atomic number, and in fact, this is what we do find. It is because the frequency increases so fast as we go up the periodic table that the inner rings of the later elements give lines in the X-ray spectrum instead of the optical spectrum. X-ray spectra do not occur as a regular thing in the form of absorption spectra, and in this they differ from optical spectra. It is worthwhile to understand why this is. When ordinary light of a frequency which an element is capable of emitting passes through a gas composed of the element absorbs all or some of it, though light of other frequencies passes through freely. The reason is that light corresponding to a spectral line of the element supplies just the quantum required to move an electron from an inner to an outer ring. The energy of the light wave is used up in doing this. The electrons involved in optical spectra are only those in the outer ring. In the case of absorption, they are moved still further out into an empty region, from which they may return at some later time in the case of fluorescence. But in X-ray spectra, the electrons concerned are those in the inner rings. When one of these is fetched out by a passing electron, it cannot settle in an outer ring, because the outer rings are already occupied by electrons. Each of the electrons that it passes on the way out repels it, and gives it, so to speak, an extra shove. The result is that it cannot rest in an outer ring unless by some exceptional stroke of luck, but has to go wandering off into space. The energy involved in such a journey is not tied down to certain amounts, like the energy involved in passing from one possible orbit to another. Its place in the inside is taken by one of the outer electrons, while the outer ring remains one electron short until it has the chance to help itself from some other atom or by means of some free electron. We saw in Chapter 2 that what is called the atomic number of an element is more important than the atomic weight. The atomic number represents a fundamental property of the atom, namely, the positive charge on the nucleus. An atom with such and such an atomic number has a charge on the nucleus which is such and such a number of times the charge on the hydrogen nucleus, or the opposite charge on the electron. It follows that an atom in its neutral state, i.e. when it is electrified, has a number of electrons around the nucleus which is the same as its atomic number. But atomic weight had the prestige of tradition as a characteristic by which atoms should be arranged in a series, and the few cases, 4 in total, where the periodic table inverts the order of atomic weight were felt to be annoying. X-ray spectra, however, have given a decisive victory to the classification by atomic numbers. We saw that different elements have very similar X-ray spectra, except that the frequencies of corresponding lines increase as the square of the atomic number, approximately as we pass from element to element. This law is fulfilled just as exactly in cases in which the atomic weight would invert the order as it is in other cases. This is what theory would lead us to expect. If each step up the periodic series makes an increase of 1 in the positive charge on the nucleus, and on the other hypothesis it seems scarcely possible. The X-ray spectra, therefore, afforded a very powerful argument in favor of Rutherford's general conception of the way atoms are constructed, as well as in favor of the theory of quanta as explanations of spectral lines. The law of X-ray spectra is the same as the law of optical spectra, namely that if V is the frequency of a line in the spectrum, i.e. the number of waves per second, and H is Planck's quantum, H multiplied by V is the energy lost by the atom in the transition, which gives rise to the line in question. There are three principal lines in X-ray spectra, called, respectively, the K, L, and M lines. For any given atom, the K line has the greatest frequency, and the M line the least. The K line represents a transition by an outer electron to the inmost ring. The L line represents a transition to the second ring, and the M line to the third. Each line, closely examined, is found not to be single, but to consist of several neighboring lines corresponding to different starting points for the electron, but all having the same endpoint. Since we can observe the frequencies of the different lines, we can infer from our X-ray spectra what are the differences between energies of electrons in different rings. Everything confirms the theory of the structure of atoms which was suggested by the hydrogen spectrum and the facts upon which the periodic table is based. Another very instructive fact which emerges from the study of X-ray spectra concerns the fine structure, of which, as we saw in Chapter 7, the explanation is to be sought in the substitution of Einstein's principles for Newton's. In the case of hydrogen, the different lines of the five structures are so near together that accurate measurements of their distance apart are very difficult, but the distance between them, as we pass to later elements, ought to increase roughly as the fourth power of the atomic number, so that measurements become much easier for high atomic numbers. On this point, the empirical evidence obtained from X-ray spectra agrees closely with the theory developed by Sommerfeld. This theory depended, it will be remembered, on the fact that, according to the doctrine of relativity, an electron which moves in an eccentric orbit has to go rather more than once around its orbit before getting back to the point at which it is nearest to the nucleus. The X-ray observations establish this theory much more firmly than is possible by the help of optical spectra alone. It must be understood that, so far as quantum numbers are concerned, the actual orbits of electrons in atoms that have many rings are the same as the possible orbits of the one electron in the hydrogen atom. The partial dimensions are not the same. The radius of the minimum circle, roughly speaking, varies inversely as the atomic number, so that in uranium it might be expected to be about 92 times smaller than in hydrogen. The velocity of the inside electron in its minimum orbit varies roughly as the atomic number, and the number of revolutions per second roughly as the square of the atomic number, but the radius multiplied by the velocity is independent of the atomic number. To a first approximation, the mass of an electron multiplied by its velocity multiplied by the circumference of its orbit when it moves in a circle will always be A in the inmost ring, 2h in the second, sh in the third, and so on. The important thing to know about an orbit is what are its quantum numbers, i.e., what multiples of h are involved. This is just as true in regard to X-ray spectra as in regard to optical spectra. It will be seen that the electron in a hydrogen atom has, in a certain sense, more freedom than one of the many electrons in heavier atoms. There is less overcrowding and more room for migration. Under the influence of incident light, the hydrogen electron can move out to a larger orbit. Presently, when the light is gone, it can return again. But an electron in one of the inner rings of a heavy atom cannot remove at will to another orbit. If it is forced to leave its orbit, it has to leave the atom altogether. The other paths which the quantum theory permits are occupied, until we get to a considerable distance from the nucleus, whereas in hydrogen, they are vacant. Paths that have large quantum numbers, though possible in theory, cannot occur in practice, at any rate in the laboratory, because they are so large that they would cause the electron to get into the region of other atoms. In certain nebulae, where matter is almost inconceivably tenuous, the spectrum shows that electrons can travel round hydrogen nuclei in orbits whose total quantum number is as large as 30, but even in the nearest approach to a vacuum that we can create artificially, there are still too many atoms for such large orbits to be possible. That is why there is a limit, in practice, to the number of lines in the spectrum of an element, although, in theory, the number of possible lines is infinite. End of Chapter 9.